B due to a wire segment. 1/4 of a circular loop of wire carries current I as shown in figure. The current I enters and leaves on straight segments like this. So enters from here and leaves from here. And the straight wires are along the radial direction. So if you have a radius, the straight wires are along the same direction from the center C of the circular portion, and find magnetic field. So this circle is right at the center of this C, or center of the circle is right here, and we are trying to find a magnetic field at this point C. Okay, maybe I can go ahead and start. It's the same thing. So it's like dB is equal to mu0/4 pi, the current, which is the same everywhere, dl cross with r hat divided by r squared. Now we need to determine dl, r hat, and r squared. First, I want to start with these segments. They look a little bit suspicious to me. There's something we can get rid of. So for straight segments, dl is like this, and dr is like this. What is the cross product of these two things? So this is dl, this is dr. As you can see, it's going to the point 0, right? Cross product of two parallel vectors is 0. So dl cross r hat is 0. So no contribution from there. So we only need to consider this portion. So for that portion, I can also, I need to use a little bit right-hand rule. So this is my dl. Let's choose this point, and let this be my angle, theta. So this dl is, the direction is like this direction, and the magnitude is, it's like r d theta. Simple circle. And now I need to do this right-hand rule, hand magic. So like first, my fingers are going along here, and then my fingers will go along here. Then if I stick my thumb out, I think it is going to be into the page. Right? Start with dl, curve your fingers like this. So start with dl, curve your fingers. So it's going to be into the page. So dl is this, and dl cross r is into the page at every point in this quarter circle. Yes, sure. So I'm trying to find the direction. So magnitude is r theta. Like dl is basically this radius times the angle. That's simply the segment length, which is always radius times d theta. And I'm going to integrate over d theta. But now I want to also determine the direction. And the direction is like right-hand rule, right? Right-hand rule says start with your fingers along dl, like this, and then curve your fingers along dr. In this case, dr is along here. The vector from this to this point is along here. So if you imagine your fingers starting like this and going like this and sticking out your thumb, your thumb is going to be into the page. So now I think, integrate. So B is, let's take out constants like this. And I think this is 4 pi. So this is r d theta. Okay, this is actually bigger r. Let's use it. And this is also r, but it is squared. So this thing is mu0 I divided by 4 pi 1 over r. Oh, okay. I need to put the integral. Integral is theta. My theta goes from 0 to pi over 2. So So this thing is pi over 2. So B in this case is going to be pi's cancel 1 over 8 mu 0 I over R. I think something like that. And the direction like into the page. So let's continue with problems. So this is the first suggested problem. So a triangular loop of side A, okay, it's like a triangle and each side is A, carries a current, it seems like counterclockwise, like this. And if this loop is placed at a distance D, like this much, D, away from a very long straight wire carrying a current I prime, okay, this one is I, this one is I, this one is I prime, determine the force on the loop. So maybe I can start with like what B was for a straight wire. It was simple. B for a straight wire was equal to exactly like what we talked, mu 0 over 2 pi. The current, which is straight wire, is I prime in this case, divided by the distance R. So I think there will be forces in different segments, right? There will be force in this segment, there will be force on that segment, and there will be force on that segment. And let's call this segment F1 because it's easy to calculate. Maybe I can write it something like that. Entire triangle is something like that. Maybe I can even put a triangle here. So this one is F1, and F1 is easy to calculate because the distance to the wire is constant, so this R is constant. So let's write this one first. So I will call it F1 is equal to mu 0 over 2 pi I prime and I, and there is like the length of little straight segment divided by the distance D. So that's the first one. So in the second one, I will have to work a little harder. So let's just, so the distance is changing. So the B field here is different from B field somewhere else. So the trick is to consider a very small chunk so that B is constant and we can use this first formula we have. And for that, I will do something like that. Let's set up a coordinate system. Let this be X, Y, and Z. And I want to choose this little segment where B is almost constant. And I want to look at its distance, which is Z. And this one, okay, I need to zoom in really close to see what's going on here. This one, okay, this is something like that. This one is, so the L, and there's like some segment here, actually, it's right on top of here. There's like DZ. And the angle in between these two is, okay, if this is 30, this one, okay, I think I can shift this a little bit. So this one is DZ, this one is DL, and I'm trying to write DL in terms of DZ, and this is 30. So DL times cosine 30 degrees is going to be equal to DZ, okay. And cosine 30 is, I think, what? Square root of 3 over 2. So let's keep that in mind. So I want to write F2 is, okay, mu 0 over 2 pi I, okay, maybe little piece contribution dF2, I prime I times it's going to be dl cross, okay. Now the B, the direction of B is what? dl cross B is out of page. I think it's like x hat. And I'll divide this whole thing with, I'm trying to use this formula. F is equal to I, L cross B. L is in that direction, like this. B is out of page, like this direction. So what is this going to be? Like L, B, I think it's going to be this direction, right? If I put my hand like this, I think it's going to be this direction. And the nice thing is every little piece is going to be in the same direction, so I can put something like that for total F2. And they are perpendicular, so I can just forget about cross product and just write it like dl. So this is dl, and the distance is z. Good. So one more time, it's like I use B is mu0 over 2 pi I prime over R, and F is equal to I L cross B, and L I just set up to be along this little chunk, and B is out of page, so F in total is going to be in this direction. Now I need to do this integral. So my dl is equal to 2 over square root of 3 dz. Then F2 is equal to, let's take the constants out, mu0 over 2 pi I prime and I. Integral dl is, okay, this is 2 over square root of 3 times dz divided by z. Let's see if I missed anything. Seems like correct. And the limits of integral are going from, okay, the first one is from going from d, and the last one is d plus this perpendicular distance, but this perpendicular distance is like what? A over 2 square root of 3 times a over 2. So this is d plus square root of 3 times a over 2. All right. We can integrate that. That's a simple integral. That's basically, maybe I can just write the integral first. So this one is, okay, there's like an overall square root of 3. This is, what is the integral? Log, right? ln z, and limits are from d to d plus square root of 3 over 2a. And if I use ln's properties, this is going to be 2 over square root of 3 ln. This is, I think, 1 plus square root of 3 over 2 times a over d. So the last segment, okay, I don't need to calculate the last segment. I already see they are symmetrically related. So this current is going this direction. I just change the current this direction. I can take this entire thing and rotate it here. So there's going to be some F3 and that in that direction. This is just, I'm using the symmetry not to calculate everything again. So it's going to be something like that. This is F2 prime, let's call it. And they're like, they have two contributions. They have like horizontal components which will cancel, and their vertical components will add up. And for the vertical component, I need to calculate this angle. So this angle is, okay, I need to think a little bit, but I think it kind of looks like 60 to me if I was to guess, right? Maybe 30, right? This is going to be through a triangle. This is like 60, then this is 30. Yes, that one should be 30. This guy is going to be 30, right? Then F, let's call it F total is equal to this guy. Let's copy, paste, minus 2 times cosine 30 is 1/2 times mu 0 over 2 pi I prime I and 2 over square root of 3 log 1 plus square root of 3 over 2 a over d. There are some cancellations. Okay, this 2 goes with this 2. And if I combine everything, this is going to be something like this. Mu 0, oops. This is mu 0 over pi and actually let's put 2 pi I prime I a over d, a big parenthesis, 1 minus, I think I need to compensate 2 over square root of 3. Maybe not. I think this one is not necessary. Something like that. But you should check this. So that's F total. And the direction is, I think you can argue for yourself. This one is going to be stronger from these guys. I think it's easy to argue if this guy is like bigger than us, smaller than 1 or bigger than 1. But I guess it's going to be down in total if I were to guess. All right, maybe I can continue. So a wire in a plane has the shape shown here. 2 arcs of a circle connected by radial lengths of wire, like these arcs connected with these 2 pieces. And you'd like to determine B at point C in terms of R1, R2, and theta. And I think the C is in the center of these circles. These are concentric circles, and you're trying to find the B at the center of these 2 circles. So again, let's just start with cutting out some unnecessary pieces from the problem. So what is the contribution from this and that? So maybe I can write first Biot-Savart law. It says dB vector is equal to mu 0 over 4 pi, the current, and dl cross with R divided by R squared. So for here, dl and dr, dl is the length of the segment, dr is the vector from the current to the point of interest. They are parallel, so the cross product is 0, exactly like you write. Yes, thank you. And for here, dl and dr are anti-parallel, so the cross product is also 0. So I don't have to worry about these 2 points. For this point, I think first let's determine the direction. So I just use the right-hand rule. So this one is out of page. I just use the right-hand rule here. This one is into the page. So this total magnetic field is going to be this minus this. So let's calculate these each pieces separately. So D, okay, let's call this B1 for radius R1 is equal to mu 0 over 4 pi, the current I, dl is, okay, R d theta, which is R1 d theta actually, divided by the distance is R1 squared. I cancel these. And I find something like that. If I integrate, B1 is equal to mu 0 over 4 pi I theta divided by R1, and this is out of page. Or maybe I can put like something like that. Similarly, the other one, the B2, exactly the same, mu0 over 4 pi I theta divided by now R2, but the current direction is flipped, so the magnetic field will also flip, so this is going to be into the page. Then total B is going to be equal to mu0 over 4 pi I times theta 1 over R1 minus 1 over R2, and I would say the total direction would be out of page, because I expect this guy to be bigger than this guy because R1 is smaller than R2. I think this one is short. Let's do this. A very large flat conducting sheet of thickness T carries a uniform current density J vector throughout, like here. And you'd like to determine the magnetic field, both magnitude and direction, a distance y above the plane. And we want to assume the plane is infinitely long and wide. So the plane is something like that. Maybe I can do this here. It's like a plane. Other one. Oh, this is like this. This is like that. And let's look at from here. Let's look at the infinite plane from here. So the current is going to be towards us. And the thickness of this guy is given to be T. And we are trying to find magnetic field at point P, which is a distance y away. What law should I use? Any suggestions for me? What is the keyword for this problem? What should we use? What is this problem trying to do? Biot-Savart, yes. We can use Biot-Savart law. Thank you for the suggestion. Like we can take a little piece of current, put like a vector from this current, and we can write mu0 over 4 pi, the current, whatever that region is, going to be dl cross r hat, and we are going to set up r squared. So we'll have to do this integral. Is there like an easier way? Is there a way that I don't want to, that I don't have to deal with this painful integral? So what was the Gauss law for magnetic field? Gauss law for magnetic field. Does anybody remember what it was? Yes, Ampere's law. Thank you. So I will use Ampere's law. I can definitely solve this problem exactly like you suggested, and I can do the integral. But I think at the end of this exercise, nobody would stay here. So let's just go through the Ampere's law and see how simple it is. So I need to choose an Amperian loop, and I'll choose it like this. So that's my Amperian loop. And for finding the direction of magnetic field, I use right-hand rule, and I know magnetic field is going to be along this direction, no matter where you go. And here it's going to be in this direction. So if I choose like an orientation like this, that's my Amperian loop. So B here, whatever happens, is exactly like the B's here, but the directions are switched. From here to here, I have like a reverse direction. So whatever I calculate from here, it's going to be canceled with this one. Also, actually, even for tiny chunks here, B and L are perpendicular. So actually, even like small chunks are going to give zero contribution. But I don't need to know that. So I need to just do this and this. So what is Ampere's law? Ampere's law says line integral around a closed loop of magnetic field should be equal to mu0 times total enclosed current. So the line integral will split into 1, 2, 3, 4 pieces. And I said these 2 pieces will not contribute, so I only need to do these 2 contributions. And for these contributions, I have like, let's call it dl dot b. This is bottom plus dl dot b top should be equal to mu0 times I enclosed. But the bottom and top are exactly, I mean, magnetic field is changing the direction, but L, the loop direction is also changing. Magnetic field is here, the loop direction is also changing. And the B is constant, so I can take it outside and just call this length, whatever it is, let's call this L. So this integral will be B times L plus B times L is equal to mu0. And now I need to calculate the total enclosed current. Total enclosed current is current density times area, and area is L times T, the thickness. Cancel these L's, and my B is equal to 1/2 mu0 JT. Okay, and its direction is like this. According to this picture, it's like this here and like this here. All right. Last question. Helmholtz coils are 2 identical circular coils having the same radius r and the same number of turns, separated by a distance equal to the radius r and carrying the same current I in the same direction, like this. There are some number of loops, and the currents are in the same direction, and they are separated by a distance r. They are used in scientific instruments to generate nearly uniform magnetic fields. A, determine the magnetic field B at points X along the line joining their centers. And let X is equal to 0 be the center of one coil, and X is equal to R at the center of other. So this is X is equal to 0, this is X is equal to R. Okay. So I think we calculated the loop. So let's just copy this. I think somewhere here we calculated the loop here. So this is the magnetic field. I'm just going to copy this. Okay, let's copy, paste. So this is the contribution from here. So this one, I use the right-hand rule, wrap my fingers around the circle, and magnetic field from this guy is going to be like this. Magnetic field from this guy is going to be the same direction, right? I think something like that. And I need to, right? So I do this from this direction. So the total is going to be what? The total is going to be their difference, right? Okay, if I can write, yes. Need to write the other one. I actually want to, I think they are in the same direction. So if I have a loop and like this, I think the magnetic field is always like this for both of them. So I'm going to add these 2 things. So B is equal to the first one, and the second one is going to be exactly the same, except, so I need to set up a coordinate. So if that's X, this one is R minus X. So I will replace every X with R minus X. So I'm good to go. This thing is something like that. Actually, even R squared, I can take it out. Let's not worry about that for now. R squared divided by R squared plus, replace R with R minus X squared to the 3/2. Okay. And that's P, and the direction is like something like that. So this is A. I just copied the circle. And now also I need to account the number of coils. So the current is I, but there are like n loops. So I'm going to multiply this with n. So this is A, determine the magnetic V at points along the, okay, this one is we got. We show that the field midway between the coils is particularly uniform by showing that dB dx is 0 and d square b dx square is 0 at the midpoint between coils. So we need to take some derivatives. So let's do this. So, okay, this thing is equal to, maybe I can simplify a little bit. Take this guy down a little bit. So I'll write this as n times I times the constant r square is out. So I can delete these r squareds. And this is going to be 1, and this is going to be 1. Now I can pull it back. Okay. Now let's take some derivatives. B dB dx is equal to this constant, whatever it is. We don't care about constant. Actually, let's write the constants too. Mu 0 n I r squared over 2. So the derivative is what? Minus 3 over 2 times 2 times x divided by, so this whole thing to the power of 5 over 2 minus 3 over 2 times r minus x times derivative of minus x is minus 1 divided by this whole thing to the 5 over 2. This is, let's call it A, let's call this one B. They are different. And if we put x is equal to 0, we need to put, sorry, x is equal to r over 2. A and B are going to be the same. So then this whole thing is going to be something like that. Cancel 2's, cancel 2's. So this minus going to give me a plus. So this whole thing is mu 0 n I zero n I r squared over 2. So this is minus 3 times r over 2 divided by r squared plus r squared over 4 to 5 half plus 3 r minus r over 2 is r over 2 divided by r squared, r minus r over 2 squared is r squared over 4. Again, this is also 5 over 2. But this whole thing is basically 0. Good. Because they are the same. You just cancel this one with this one, so it's 0. Okay. Now I need to take the second derivative. Let's do this. D squared b over dx squared is equal to, so mu 0 n I r squared divided by 2. Okay. So I had minus plus 5 over 2 times 3 times x times 2x divided by this thing is r squared plus x squared to power 7 over 2 and plus 3. Okay, I need to take the derivative of this guy. I take the derivative first, and now the other one is simply what? The other one is simply, let me put this a little bit like this. So derivative of numerator is basically itself minus 3 divided by this a, whatever it is, 5 over 2. This is plus. The other one is derivative of this guy is also minus 3 divided by, so b to the 5/2. And finally, plus 5 over 2, 3 times r minus x times r minus x times r minus x times 2 times minus 1. Divide this whole thing with b to the 7 over 2. Okay, a lot of factors, but I think they'll all cancel. For example, this one goes with this one goes with this one, and let's substitute x is equal to r over 2. So this is going to be mu 0 n I r squared over 2. A and b are going to be the same if they are at x is equal to, so okay, let's write it, plus r squared over 4 5/2. So the last one is what? Plus 5 times 3 times r squared over 4 divided by r squared plus r squared over 4 to 7 over 2. And the next one is minus 3 over the same thing, r squared plus r squared over 4 to 5 over 2. And last one is plus 5 times 3 times r squared over 4 divided by r squared plus r squared over 4 to 7/2. Now I want to take this factor outside and let's see if everything cancels nicely. So then, okay, this is equal to some factor times minus 3 plus 15 r squared over 4 divided by, okay, r squared plus r squared over 4, 5 over 4 r squared plus the same thing, 15 divided by, okay, r squared over 4 divided by 5 over 4 r squared. And so this r squares cancel, 5 over 5, 5 over 5, 5 over 5, this one. This guy is 3, this guy and this guy is 3. Okay, good. So you can see if you had the fate, everything canceled. So this is 0. Oops, unfortunately, this is a little bit outside. Okay, so basically, if you take the derivative of this, you have two terms. If you take the derivative of derivative, there are 4 terms, but they pairwise cancel each other. and you have a 0 at the end, which is nice. I think I'm going to finish it here. All right, then thanks for coming. I think that's the end. I'll see you guys on Monday.